So let's get started. So because of time, I don't really review what we have done in the first class. So first topic. So topic one, just 1 minute quickly review. I mean, we just cover every. I think we cover Excel, right? We also cover how we do summary statistics, right? We do how to do mean, median, mode, dispersion, right? And then we cover range, inequality range, standard deviation, variance, coefficient variation. For the shape, we have kurtosis, skewness, and also we have correlation coefficient and covariance. Okay, and now as we see that that is a data, and if you try to extend the data to the case where we want to take the data, what we learn from data, right? We look at the mean, median, those kind of things. Can we extend it to general knowledge? Okay, we want to generalize it to a things we've learned. We have to understand probability, right? Because the thing we got is part of the whole picture, right? So the probability we involve because we're just getting one of many possible outcomes when we do sampling, right? So that involve probability. So that's the reason why we have to go for probability. Okay, and so as I said, there was a time constraint. I'm not reviewing what have been done. If you need review, then please check back the video. Okay, so probability, we go straight ahead. So how do we define probability? Okay, to define probability, we need to define what is random experiment. Okay, random experiment is in the classical meaning means we know that something is going to occur from the random experiment. Okay, nothing happen is also belong to random experiment outcome as well. And the fact that is we know what might happen, we don't know which one. So is we have a knowledge, we will not be surprised by some outcome comes out. We just surprised it comes out. Okay, we know what might happen. Okay, but we actually don't know which one. Okay, only surprise us is because it actually comes out. It's not surprise it can come out. Okay, so we know what's going on there, right? Just like the back blocks, right? You can imagine there's a lottery, right? You put your hand in, pick something out, okay? You don't know what it is, but you know what kind of stuff can be pulled out there, right? Just like a box, you put number there, right? You put your hand in, it must come out a number, right? It cannot come out a rabbit, right? It's not magician, right? It's not coming, you put some, where your head comes out, there's a rabbit. No, there's nothing happened, right? I mean, it has to be something in your mind, what is possible, okay? You don't know which one. And it potentially can repeat a lot of time itself, okay? And if you can't repeat, then we really don't know, okay? So the classical idea random experiment can't say how likely this galaxy have more than one sun or more than 2 moons or we have 3 Earths. No, I mean, we can't really, because we can't repeat potentially as far as I understand, right? What's probability have? There are many of, I mean, how likely is a multiple universe? I mean, we can't answer this question because it can't really repeat, right? But what can be repeat, like toss a coin, roll a die, something you can repeat. Okay, later you will see why repeat is important and why we have to know what are possible is important. Okay. Once we know what's random experiment, still very weak, but from example, you know what it is. Okay. And outcome will be one possibility of the random experiment. Okay. For example, tossing a coin, head or tail are 2 outcomes. Okay, it's told then rolling a die is going to be 1 to 6. Suppose you're rolling a 6-face die. Okay, so that would be the outcome. Okay, basically it's the random experiment, and one outcome would come out of that. Okay, and event will be a group of outcome. Okay, and this is usually we care about event rather than outcome, right? Just like if you care about a die, you care about even number, you care about outcome, right? And for example, random experiment can be the rainfall level, right? And it can go from 0 to any positive number, right? And the event you care would be when the rainfall is more than 100 millimeter or 80 millimeter, so you don't have to go to school, right? The red storm or the black storm, so on and so forth, right? So event is something you would care, right? So there's group of outcomes, right? Suppose you are going to roll die, right? And you are going to bet on even number, and that is all you care, right? Or horse racing, you may buy the places, right? So you don't actually care whether the horse you're going to bet on is first, second, or third, right? As long as it's 3, then you win, right? So you care that event. So that's why group of outcomes, okay? And this event is usually what we care, right? Sample space, okay? As we said, random experiment is we know everything, right? So we know all possible sample space, right? All possible things can happen. Say like toss a coin, head and tail is the sample space, right? And 1 up to 6 is the sample space, okay? And to remind you again, when we talk about classical probability, we know what might happen, okay? We just don't know which one, okay? So that would be the case, okay? And that is the classical definition you learn from your high school, right? And suppose you repeat random experiment many times, right? So that's why you have to repeat, right? And that's why I said, well, how likely that we have 2 moons? How likely the asteroid is going to hit the Earth? Okay, what's the probability that dinosaur is going to exist now? I mean, this thing cannot repeat, so we can't answer. But suppose we're able to repeat that, right? And then you can calculate the ratio, right? How many outcomes that favorable to event and over total number of experiments you conduct, right? So that would be the probability that's defined from empirical sense, right? You repeat tossing a coin million times, for example, right? Suppose the coin is fair, you expect half of the time is head, half of the time is tail, right? So around half a million is tail, half a million is head, right? And we define the ratio, right? Because half a million over 1 million is 1/2, right? So basically just potentially can repeat it and then you can sign it, okay? So that is what we mean by probability. Is that clear? I think you have learned that anyway in your high school, but we have to define properly. And the definition have to be very careful if something can be repeated and there's no surprise over that, right? Because the thing is, if potential can be repeated so many times, then of course you basically you know all possible thing can be come out of that. So that is not something a big thing, right? As long as you are able to repeat in principle, right? And then you know everything, all right? So that's the idea. Okay, let's see the example, then there would be no confusion because this is the way we learn math, right? From definition, it's easier to look at examples. So roll a die or consider fair dice, and 1 is an outcome, right? And 2, 3, 4, 5, 6 also outcomes. Okay, and we would group everything together is what we call sample space, right? 1 up to 6. And the way we write this, we will use the set language. Those of you who haven't learned set doesn't really matter, just the way we write stuff. Okay, we'll be using a curly bracket. Okay, and each outcome separated by comma. Okay, that will be the way that we write in probability with the event, right? So that's why later, although this look very weird, but if you learn math, this is the foundation of math, right? If you ever know the foundation, how people write math is you start from logic. And from logic, you have set theory. From set theory, you build up all the modern math. So set is essentially the most set language, like this curly bracket, this kind of writing is the most fundamental thing that if you learn math. So we just follow the most convenient way. And then you also see that in the textbook as well. Okay. And event E will be equal to the set which is collection of outcome, is 2, 4, 6, because event, there's an event, right? Because it's collection. Odd number is 1, 3, 5, right? And with large number is also event, right? 4, 5, 6. So we can define a small number, right? Also, it's 1, 2, 3 is also an event, right? Also, we can define prime number is also an event, okay? It's just bunch of outcome, okay? And probability, okay? And if the die is fair, okay, you expect actually each outcome would appear 1/6 of the time, right? Suppose you roll the die 6 million times. Each number should, roughly speaking, 1 million times for each, right? So if you talk about even number, you should expect 3 millions of time comes out over 6 million. So it's 1/2, right? 3 million over 6 million. Right? Suppose you have all same and log the same. Is that clear how you define? Okay. So remember, the definition here is define the probability comes out from the fact that it's a fair, and suppose you roll it, when you say even, when they're fair, that means each outcome is equally likely, right? So that is the meaning of fair. And that makes sense in the classical sense, okay? If you try to, this is called the Venn diagram. If you learn set theory, that will be something like this, okay? You would put the S the sample space, okay? And O is odd number, is the green circle, it include 1, 3, 5. Even will be including 2, 4, 6, and large will be 4, 5, 6. So this is the way that you represent things in a set, okay? Don't super worry about this. This is the graphical illustration. I'm not expecting you to produce this graph or what, okay? But that is how this is being represented, okay? This is standard way the probability being taught in math, Department of Math or Department of Stat, same thing, okay? Now, if you roll a die twice, and how are you going to represent an outcome, okay? And usually we represent it by pair, or to be formal, is order pair of integer, right? You have a pair, and the first number will be the first time you roll. The second number will be second time you roll. Obviously, order matter because you roll 2 times, right? 1, 2 is the equivalent to 1, right? 1, 2 means the first time is 1, the second time is 2. And the second one is 2, the other one is 1, right? And the sample space you can see will be 1, 1, 1, 2, up to 6, 6, then will be 36 outcomes, right? Because you basically can list them into a table, right? And you can see writing the sample space is very complicated, right? And sometimes we actually don't care that much. We may want to simplify it, and that's what we call random variable. We will learn after this topic, okay? Probably next week. We'll learn how to simplify our sample space, okay? For now, we just only able to say the sample space is the order pair, okay? 1 over 36, okay? And the event that is the sum of 2 die is less than 4 actually only consists of 3 outcomes, 1, 1, 1, 2, and 2, 1, because 2, 2 is not, right? So if the die is fair, then it should be 3 over 6 is 36, okay? For those who arrive late, maybe I just quickly repeat what we have done, because otherwise they will not know what's going on. Right? So we start with random experiment, which essentially said there are things we can repeat. And the experiment, every time you run it or you conduct it, there's an outcome, okay? And just like rolling a toast a coin, head is an outcome, tail is an outcome. And event will be usually the same, collects multiple outcome grouped together, we would care. Say if you care rolling a die, whether it's even number or odd number, right? Even number is an event. The sample space is the all possible outcomes. And probability would be the ratio, okay? You just take the ratio, how many outcomes that are favorable to the event over total number of experiment you're going to conduct, okay? So just to remind you again, you have to be able to repeat for this to make sense. If you can't be repeat, we can't say anything about probability. That's a classical way, okay? And here we have example, okay? And this is the way the Venn diagram is being done. And here the example is saying, if you roll the die twice, what kind of outcome you can get. And here you can easily see that it's already for, if you roll twice already, 36 outcome. If you can imagine I've rolled 10 times, the sample space would be crazy, right? So it's not manageable. So we have some way to handle that, but that will be what we cover next week. Okay. So now we learned that we are going to go a little bit deeper. Okay, is what we learned we call operational events. Okay, because this is the base. The event is going to be too simple. We need to learn how to combine event, which is called intersect, union, and complement. Looks very complicated, but it's just English. This is the logic called intersect is and. Union is just or, complement just not. So just, I mean, if you learn logic, this is, you learn set theory, this is just and, this is just or, this is not. You learn, if you learn logic from the physics in the high school, this is the thing. Okay, you will learn why they're useful, because this is the way that we build stuff. Okay, because if you want to ask the probability of certain thing happen, that thing can be very complicated. And then we try to decompose it, the complicated event, into multiple small parts. And how to build up the thing is just like and or not. It's like Lego. Okay. You want to build a very complicated object. You start from, it's very difficult to build from scratch, right? You decompose it multiple parts, and that you can calculate each part and add up together. That's the idea. Okay. That's why we need to do that. Okay. So intersection simply means that we have contains all common outcomes in A and B. Is and. Okay. Although it looks very complicated, let's look at the example that you will find it extremely easy. Okay. That is just the thing you learn in the high school, what we call finding common factors. Just common factors, right? Or we find common elements in the two different events. So suppose you roll a die once, you have event sample space is 1 to 6, right? And suppose even number event is 2, 4, 6, right? Odd number is 1, 5, 1, 3, 5. Large is 4, 5, 6, right? And even and large, how do we do that? Look at even and large. What outcome do they have in common? Okay. 2 is in E but not in L, so it's not there. 4 is in E but also in L. That's why here, right? 6 is also in there, then 6. Then you probably ask 5, but 5 only in L but not in E, then we're done. Okay, so we just find out the thing that appear both in the event, okay, in both. And similar, you ask how to do O intersect L, just to figure out things that they're same. Okay. 1, do they have an L? No, that's not. Is 3 there? No. 5, yeah, we have 5 here. And go this again. 4, no. 5, yeah. 6, no. So that's why it's 5. Is that clear? So it's very simple, just taking the common thing. Okay. And so that is the idea. That's easy to understand is if you try to draw a Venn diagram, it's simply the overlapping area. Okay. Is that clear what it is? Is overlapping area. Is whether they appear the same. Okay. So the next would be union. Remember, union is or. Okay. It's like what you do for doing the LCM, right? Common multiple. Just take everything there. Okay. Is contain all outcome. So whatever you have, you just take it out. Okay. So again, the same question. Now we ask, what is E and L, okay? So we just write everything there, okay? We have 2, 4, and 6, that's why I have here. And extra, we also have 5, so we put everything there, okay? Just write everything. And probably you ask, why don't I have 2, 6, and 2, 4 here? And no need, because in terms of set theory, repeating has no problem. There's the same. So suppose you write this the same thing. So if you write 2, 4, 4, 5, 6, 6, in probability the same thing. So the same. Just appear twice. We don't have to write that down. The same. Okay. You don't have to write. You don't have to repeat that. Okay. And for O union L, the same idea. You just write down whatever in both. Okay. Is that clear what's going on? Okay. So union is or, right? And or. So basically just like include everything there, right? Or just overlapping, right? Intersection overlapping. Union, just take out everything there. Okay. Later you see why we talk about this. It's very important. Lastly, that is called not. Okay. Not in the logic. It's just like everything but. Okay. So again, the same sample space and event. Okay. EC is everything in S but not in E. Okay. Look at this. You just cross out what is in E. That's what you have. Is that clear? So just everything but E. Right? And let's look at what is L. Okay. L is everything but L, right? Just cross out 4, 5, 6. That gives you 1, 2, 3. Okay. So now with this, then we can talk something more interesting. Okay. So this is the graph, right? Because what is in E was not in E, so outside the E. All right. But so now we are able to introduce 3 different types of event. One is called mutually exclusive, later is exhaustive, and partition. So these 3 are things that make our life easier how we do it. Okay. So first one is called mutually exclusive event, which essentially said if A and B are mutually exclusive, means if A happen, B can't happen. If B happen, B can't happen. So one will exclude the other. Okay. So one example is if you are in New York, you cannot be in London. Okay. So suppose if a boy is dating girl A, he cannot date girl B at the same time. Okay. He can date different time. Okay. If you're a good management of time, but if you're a good manager of time, then he can only date at the same time, right? He can be either in the cafe at one point of time, right? He cannot be the other way, right? Right. So and that is called mutually exclusive, right? So either if A is true, B cannot be true. If B is true, A cannot be true. But it can be A, B both are false. Okay. Only thing rule out is can't both true. Okay. You just rule out they can be both true. Okay. Mutually exclusive. And this one is exhaustive, right? Exhaustive. Exhaustive means that I list out all the possible things. So must be either A or B must be true. Okay. So that's why the union is a sample space, right? So one possible case is exhaustive is like either that's what people do, right? There's a girl, okay, have a flower, and she put a petal. He love me, he doesn't. He love me, he doesn't. Right? Only 2 possible cases, right? Either he love her or he doesn't. Right? Must be one of them is true. So list out everything, right? So this is like you're happy or not happy. Must be one of them is true. right? I don't know whether you guys are too young, but a very famous commentary for soccer in Hong Kong. One thing is like, now is the penalty kick. There are only two outcomes. One is the ball go in the goal, one is not. Okay, that is standard thing. I don't know whether you know, but that is a very famous statement. In Cantonese, that is 12碼兩個結果，一係入，一係唔入。But you guys are too young. But in my age, it's like this is a very common statement when the host has nothing to say when there's a penalty kick. But that is a standard thing, right? That's the thing. So that's basically just like exhaustive. Means either both must be true, right? So one of them must be true, right? And this means mutual exclusive means cannot be both true, and this is must be one of them is true. Okay. So here the last one, that is something is most important is what we call partition. Okay. Partition is things that is mutually exclusive and exhaustive. Okay. If it means that I say several events, if they're mutually exclusive, exhaustive, okay, it means that at least one of them will happen, and exactly one of them will happen. Okay, let me repeat. I said partition means exactly one of them will happen. Okay, cannot be more than one, but exactly one will happen. So basically, I list out all the possibility, and they cannot be both true, but at least one of them is true. They call partition. Right? And the reason why we care about partition is the way, as I said, you try to calculate that. Right? You try to calculate something happen, you will partition what you want and consider them one by one. Okay. Later you will see that is a very important way to handle things. But this is the partition means. So partition means it's like cutting a birthday cake. You cut it into several pieces, right? And they don't overlap, right? You're going to cut in this way, right? When you cut, then they're separate, right? So that is the way. Now we have sample space 1 to 6, right? And E is same, E and O is the same as before, but now we have P is the prime number, okay? And B are the, I don't know, 4 and 6. I think it's big even number, okay? First, we want to say O and B are mutually exclusive. Why? O and B cannot happen at the same time, right? If O is true, B cannot be true. If B is true, O cannot be true. But do note that if two happen, both of them are false. Okay. And second, OPB are collective exhaustive, right? Because it must be at least one of them happen, right? If one comes out, O is true. If two comes out, P is true. If three comes out, O or P are true, right? And 4 comes out, B is true. 5 comes out, O and P are true. 6 comes out, B is true, right? So everything will be there. At least one of them is true, okay? And E and O are mutually exclusive, exhaustive. The reason is at least one of them is true, and at most one of them is true. So it means that exactly one of them is true, right? E and O is just like, if E is correct, O is incorrect. If O is incorrect, E is correct, right? Knowing one will tell the other, right? If we know E has happened, O can't be happened. If O happened, E can't happen, right? So because one way or the other. Is that clear? So that's called partition. So that's, I think I just said it, right? Mutual exclusive is that most one of them happen. Mutual exclusive at least one happen. So that's why partition is one and only one will happen. Okay. So, I guess we start a little bit late. Maybe I just borrow a few more minutes before we have a break. Okay. So very quickly, before we consider the probability, comes from what? Doing experiment, right? And that means that things are really rely on the real world. Okay. So how we define probability, we want to define probability without talking about real world. Okay, so that is what we call axiomatic definition. We start from axiom. Okay, so same as what we learned from geometry, right? Geometry coming from looking at triangles and things, they measuring the how they divide the land in Nile River, right? Or in those days, right? And the thing is, they come from practice, but the Greek people, right? They try to generalize it to math, right? Without looking at the real world, right? Same idea here. We want to talk about probability without talking anything about real world. Just divide from math. So we start from some axiom, some assumption, make some assumption, then we're done. Okay. So probability here is, without talking about relative frequency, we talk about is a function, okay, that from event to number. Okay. What does that mean? It means that I have the sample space. Okay. You give me every single possible event. I give it a number. Okay. And you record probability if, okay, the following thing we satisfy. There'll be three thing. One of them is the first one. We'll talk about this for a break. Is the first axiom we have, which is what we call probability must be, no matter what you give me, the number must be between 0 to 1, right? Cannot be negative number. It make no sense. And it must be at most 1, right? Say, for example, the sample space, what we have, say, is 1 up to 6. Okay? Then you have to tell me if even number, what's the number? What is probability you assign? If this odd number, what's the probability you assign? Okay? Because when we talk about the example before, we consider fair die, right? But what about the die is not fair? How can we define? Okay? Then you have just to tell me what are the probability for this event. Okay? That you describe the whole structure. Okay? So that means that what we are going to do, apply for every single case. Okay? We divide probability by telling me that for every possible outcome, basically, right? You tell me what's the probability to that, and then we can define. Okay? But before we talk about the three axiom, actually the three axiom with three possible assumption on how you put number to event, we divide probability. Okay? The first one is it must be between 0 and 1. We'll talk about the next two next after the break, but shouldn't be difficult because they are just assumption, and the assumption actually has this by axiom means we don't explain why this is true. We just take it as given, and we think this is natural. We don't ask further. That's the math, right? Math is like you take some axiom, that's it. We just don't ask why is it true. Okay, that is true. I mean, we take it. Okay, let's have a break of 10 minutes today because we have the time constraint. Okay, let's resume at 3:32, and then we can continue. Because we go rather quick, and those of you who come late, please feel free to ask me a question. I go around. I guess we should resume. Because time. We should resume. Sorry for 10 minutes break, but that's not our fault, right? It's the bus problem. So now go just to remind you what we are doing is we're trying to define probability. Okay, we don't want to talk about probability from calculating rerun experiment many times, right? Then it's not very precise. Okay, we want to come up with the mathematical structure or the properties that we can understand how we define what do we mean by probability. Okay, it's the way that you give me an event, I give you a number. Okay, and what kind of number you can give me? You can always only give me 0 to 1. Okay, give me whatever event I told you, you give me a number. So the first axiom. Okay, cannot be negative, cannot be more than 1. Okay, must be between 0 to 1. The second thing is the sample space, you must give me 1. Okay, that's trivial, right? Because that means that we know what's going on, right? I mean, we have complete description, right? It must be one thing in the sample space happen. So it must be one, right? So there's no surprise, as I said, right? Same as what we call random experiment. We know all possible outcomes. Same idea here, right? So, okay, remember the event must be between 0 to 1. The whole sample space must be 1. Okay, very natural. So the third one is most technical, but of course, that's the most important one. It derives everything we want. The third one is the following. If events are coming from mutually exclusive outcome, okay? So A is equal to 1 up to N, okay? And when O1 happen, O2 cannot happen, right? Mutually exclusive, right? So O1 one of them will happen, okay? Sorry, not one of them. If one happen, the other cannot. At most, one of them will happen. Okay, that's called mutual exclusive. Remember, remind you, that means the interset of anything is empty. This is called empty set. There's nothing. There's no common thing among them. Okay. Now, what do you mean by probability? It only means the following. Any event, if it is, you can write as union of this, right? Because that is what it means, right? It's union of this, right? That's called the event, right? And the only thing that is important here is if they are mutually exclusive, you can just add them up. Okay. So if an event consists of two outcomes, A and B, and A and B can't happen at the same time, it simply said the probability of this will be just A plus B. Okay, let me repeat. It's very important because that is the building block of the probability, because we only rely these three axioms to build up everything we learn. Okay, that's called axiomatic definition. It's just we define in this way. Anything you define it consistent with have this property, we call probability. That means that this is the only thing we need for define probability. That means admit anything you want. Okay. If an event can be written as union of, say, this outcome, and they're mutually exclusive, then just add them. That means it's additive, right? So add them up is fine. It's just like the whole park. You can cut them into multiple parts. That's it, right? Say, if a roll a die, even number can be decomposed into 2, 4, and 6, right? They're mutually exclusive, so it must be sum of probability having 2 plus probability 4 and probability 6. Okay, so that is the idea. Okay, just sum of them. So from this, we would build all probability property. Okay, we all start from this 3, and that's it. Okay, anything that is consistent with the function that you assign, the number you assign to the event, as long as satisfy this, then it's probability. Okay, for example, the following. Okay, we define it for the fair die. How we define for fair die? Okay, we have a sample space 1 up to 6. Okay, axiom 2 means the following, right? Probability of sample space is 1. Okay, the next one, axiom 3, tell us 6 outcomes are mutually exclusive, right? So that means that sample space can be decomposed into 1 up to 6, right? So that means that I can just add up, right? And from axiom 2, this is 1, right? This is 1. And now, here's the assumption. If die is fair, okay? It need not be fair, okay? Suppose it's fair. If unfair, you can make other assumption, right? Suppose it's fair, then the probability will be same, okay? And because equal to 1, they are same. So that's why 1/6. Okay. 1/6 is by construction because you say they're same, right? But you can make other assumption like 1 is 2 times, then 2, 3 times, then 4, and so on and so forth. We can make some assumption, then you can get another structural probability, right? So, but that means that our definition is very general, right? And we can write the probability of even event. Even is 2 up to 6, right? So that's why we can do this, right? Just like even, we just add up 2, 4, and 6. Okay. So don't worry. I mean, that's not very natural. There's nothing new to learn here. Just applying the concept because you know already, right? But probably there's nothing new to be learned here, but let's see how we learn from this one, right? This is very natural. We know it already. So a technical note is actually why this make a big thing here, okay? The problem, actually, if you learn math, the problem is this actually extend when we have infinite number of outcome. And this is where this probability bites. Means that if you union and you infinite outcome is still adding, okay? If you know math, that is a big thing, okay? This is a big assumption here. And why is it important? Because we're able to, if this is a not continuous, that's fine. That's natural, right? Suppose you have a cake, okay? You cut it 3 area, right? Then some of the 3 pieces should be the cake, right? That's no problem. But the problem is we cut it infinite time, okay? Whether combined together is still the same, not clear, right? Because when things go to infinity, things can be very crazy, right? So, but that is the only thing. Ensure that even if you cut things infinitely, sum them up is still the same. So that is, this is biting. But when you're and am I talking about finite number of outcome? There's no problem. And of course, in our class, we focus on finite number of outcome in most cases, right? So it shouldn't bother you for this axiom. But in order to say things continuous, infinite outcome, then we need this axiom. So that's why actually this thing is, I mean, of course, for you to understand infinity is a very difficult thing, probably if you don't have practice. But indeed, for mathematicians, they take this hundreds of years to develop this. I mean, this is called the Kolmogorov axiom of probability, invented in, I think, 1920 something. But probability has been exist since Bernoulli, 1600. So it takes mathematicians 300 years to come up with these 3 assumptions, probably 100 years for each. But you can imagine it takes very long time to do it. So it's understandable. You don't understand, it's fine. Okay, you don't have to understand it because you don't have to understand it for it work. But you have to see why we have to define things in this way, right? Because if infinite outcome, how can you define normal frequency, right? The infinite outcome, how can you count? How can you do the ratio? Is it meaningful, right? So, but anyway, we'll sidetrack all this thing, just assume everything defined nicely. But this technical note, but since we're B school, probably it's okay. Don't forget about, we can forget about it. That's why I put the black here, you can forget. For those of you who just come in for this class, the black thing, you can ignore, okay? And the purple thing, it's better to know. If you don't know, come back, it's fine. You know where to find. The most important thing is look at the green. You know what's going on. Because example, because we're B school and this class focus on application, you're able to do the green. If you don't know the green, then I mean you may fail your exam. Okay, the green thing you should know. Okay, the black is okay. The purple, then you should this is the thing that you should know, but the most important is the green. Okay, make sure that you know the green thing. Okay, and here, because of the axiom, actually we can derive a lot of probability rule. Okay, this is the rule that we call complement rule. This you learn mathematics, so you learn probability. This is the main rule that is very useful. Okay, I have an probability A. Okay, this is something I want to calculate. Okay, and this A can be very complicated. Okay, it's very hard. Okay. But what can we do? Okay. We can find its complement and calculate probability, then make our life easier. Right? That is how we do. Right? That sometimes is like same as when we go to restaurant, right? Go to restaurant, the menu have many dishes, right? Then sometimes you don't know how to do it. You just take away what you don't like. Then what's left is easy. Right? Same idea. Okay. Now we can prove it, but we don't want to do it. I mean, the proof is here, but I don't want to go for it. But let's look at this example. Okay. If you want to look the proof, this is very simple. You can just do it with some math, you can do it. Okay. But I don't bother with it. Let's look at the example because it's not complicated. Okay. So let's look at this example. We want to look at probability that the face value is less than 6. Okay. You roll a die. Then what is the probability is less than 6? Right? So the straightforward way is you have to count of them, right? Roll a die is 1, 2, 3, 4, 5, 6. Less than 6 is just 5 outcome, 5 out of 6. Right? It's a fair die. Right? But the another way to do it is look at its complement. Okay? Less than 6, because at most it's 6, right? So the complement with just 6. Right? Is that clear? So that means the complement is just it's equal to 6. That's 1 over 6. So 1 over 1 over 6 is 5 over 6. Okay. So you see this is rather trivial, probably. So let's see the example now. Another example that this is 6. We know outside 6, then we can calculate inside. So maybe I give you the example of this. Okay. Here is a little bit technical, but this doesn't make a big difference. If your sample space can be partitioned, okay, basically you have sample space, you cut them into small parts, okay, you just add them all up is equal to 1, right? Because this is what we call the is the axiom 2 and 3. But anyway, so why is important? Suppose you roll the die twice, okay, and what's the probability having the sum of the result is less than 11? Okay, looks complicated, right? But you know sum of the die must be 2 up to 12, right? So let's consider AI means the sum of the two results is I. Okay, and if you have the sum is 2, you cannot be 3 or 4 or 5, right? So A2 up to A12 is a partition, right? Either you have 2 or 3 or 4 or 5 up to 12, right? So asking less than 11 actually means the union of A2 up to A10, right? If you do direct calculation, A up to A10, then you have to count 8 times, right? But if you do the other way around, only care about 11 or 12, and do a subtraction would be easier, right? Because A12 means you get 12. The only possible is 6 plus 6, right? Just only 1 over 36. How you can get 11? Only 5 and 6 or 6 and 5. Only 2 over 36, right? So take 1, subtract that, you're done. Rather than you add A2, A3, A4, A5, A6, A7 up to A10. So you can see it's much easier when you're calculating this way. Okay. So that is why it's the thing, right? Either you can calculate what you want, or you can calculate what is outside, subtract, you get the inside, right? So that is the idea. Now we have more rules. I mean, of course, if you learn it from high school, the probability, that is something you learn already. Okay. So that's why I'm slightly quicker than usual, because this is something We just learn it because we have to let you know what probability is, right? So, but we don't actually go too deep into this one. Okay, that's something the best we are going to learn. So, axiom A said if A, B are mutually exclusive, we just add them together, right? But what if this is not mutually exclusive? What can be done? Okay, so that is what we call the addition rule. Is you add them, but you take away the overlapping part. Okay, and to understand this formula, that's very simple. You learn that from your kindergarten. Okay, I convinced you this is kindergarten formula. Why? Look at the graph. Okay, look at this example. Maybe before I convince you kindergarten, let's go to the example, then that will make sense. Okay, this you can later see this is a kindergarten example. Okay, so I roll a die once. Okay, what's probability having even number or a number greater than 3? Okay, let's call even number is A and even number is 2, 4, 6. Right, fair. And B is greater than 3, so we have 4, 5, and 6. Okay, so or means union, if you still remember. Okay, we want to ask A union B. This is something we want to find. Okay, now how do you find that? Okay, A union B you can do directly. A union B, just take all the element there, will be 2, 4, 5, 6. Right, direct approach. And there 4 out of 6, then it's 2/3. So that's very simple. Right, but now suppose you don't use the direct method, use indirect method. Okay, do it because I want to find the intercept, which is n. Okay, even number bigger than 3 is only 2 numbers, 4 and 6, right? Because only 4 and 6 appear in both. Okay, so what we're going to do is, by definition, by constant, is union is A plus B minus the intercept, right? So it's 3, 6 plus 3, 6 minus 2, 6, right? Equal to 4, 6, and the same as 2/3. Okay, so this is called addition rule. Okay, that actually this rule relay what mean by union and intercept, right? The complement rule explain why we need complement, and this rule relay the intercept, right? Because the intercept and complement are related in this way. Okay, and probably you look at this question, right? A is even number, B is large number, right? You have 1, 3 outside, right? If you have sample space, 1, 3 is outside. I didn't draw it, but you will see the probability A what did I do? A union B, okay, is asking, right? If even is asking this, how many things in this right? You have, right? What's the area of this? Let me draw it. It is not a very good. Let me draw in the whiteboard. Okay. So the question is A, right? And this is B. Okay. And this is what? A intercept B, and this is A union B. Okay. What mean a kindergarten is because the following, right? If you have A plus B, okay, and actually you add up will be bigger than the green, right? because you double count this area, right? Subtract this guy, right? Will give you this, right? That's what you learn from the kindergarten, right? So that's exactly what it means, right? You know this, right? Kindergarten, overlapping, take away, double count, right? Take away. That's it. That's what I mean, right? Kindergarten math, not math, kindergarten drawing. Is that clear? Okay. So let's go back to this, right? Kindergarten drawing, right? A union, right? It's just A plus B, right? Take away the pink area, right? Now, this is the example that you often seen how we use this, okay? This is the table, as we said, the condition table in the first class is you have 80 students, either they're male or female, or they pass exam or not pass exam, right? Represent this is, consider the case we have 15 here means we have 15 male students who pass the exam. This means we have 20 female students who failed the exam. So that is what it means, okay? And you can see add up to 80 because we said 80, right? And this row is sum of the row, column, sum of the column. This subtotal here, okay? I hope every number makes sense here. Now, the question will be the following, right? This is the data you have, right? The answer is, the question is, if I randomly draw a student, okay, how likely it is male or you pass exam, right? So or means what? Union, okay? And all this is intersect is and, right? The question is asking the union, right? Or, okay? So how can we do that? So use the formula, right? This is the same thing, right? You find the male, right? And you do the female, sorry, male in the past, right? And then subtract the intercept, right? So first find probably the male. How many male you have? 40, right? That's why 40 over 80, right? What is the pass? How many pass is here? 35. I should use blue because that might be better. Blue pass, right? Pass is 35 over 80, right? Why 80? Because the 80 student, 35 of them are pass, right? This is the probability that randomly drawn students are pass, right? This is randomly drawn, they are male. So now the question is here, right? Purple, pink, male and pass, right? Male and pass is here, 15. So it's 15 over 80. So this number. So now we want that thing, right? Male or pass, right? So just the first element is the red, right? And adding the blue element and subtract from the pink is the green, right? This is the guy. Is that clear? Just kindergarten, nothing new. Right? Of course, if you don't like that, that is something you learn. It's not that difficult as well. Is who are the people that male or pass? That's simple. These three, right? Is that clear? That's why 15 plus 20 plus 25 are 60 people that all pass. They give the same answer. Okay? So that illustrates how you can do that. Okay? The reason that we need to do that is because, well, you can say, well, why we do that? Because this, look at the table, we're done, right? But very often we don't have the raw data. We only have this number. Then you have to calculate this, right? Then that means that we don't have to go back to the raw data. We can just directly calculate. Is that okay? Any question? I know we're going a little bit fast, but But that's, I mean, if you learn from the, you learn probability before, then you would be easy. I mean, I hope everyone have learned probability before, right? Some complete zero. Oh, that's okay. I mean, don't worry. This is the only chapter that we actually calculating probability directly. Okay. And later you notice it's not something that, the only thing you probably remember, probability is just number from 0 to 1. And probably that is the thing. And then you use the complement rule. That would be the thing we use. It's like, thing on the left and thing on the right will be complement. And that would be the main thing. If they are disjoint, then just add them together. Basically, just like what you learn in the, what you learn in your kindergarten will be sufficient. But we have to, I mean, as a college course, when we have to cover all the bases, because some of you actually are the QFN student, or some of you will continue to study this 2021, then I need to give them foundation for that. Okay. And as long as you know how to do the assignment, or you understand the example, then should be fine. Okay. This one is called the total probability rule. Okay. Again, this is nothing special, same as what you learn from kindergarten. Okay, let's see. I convince you this is a kindergarten formula. Why? Let's see again. This is an example that you always have during the Mid-Autumn Festival. Okay? Suppose this is a table. Yes. And we have something that probably you want to eat or not. This is the mooncake. Okay? And this is called the mooncake A. Oh, I should use a color. Okay. And now I have a knife. I just cut. I don't know. I just cut it into 2 halves. Okay. The left hand side I call B. Okay. If I call left hand side B, the right hand side will be B complement. Right? Maybe I use another color to make it nice. Sorry for my art skills. I told you, I mean, art is something that I don't do very well, very badly. Not do well, but very badly in the school. So that's why you can see very bad. So now I said this is kindergarten thing. Okay, why? A can be considered as 2 parts. One is A with B. The other one is A without B. Okay, let me say it again. This A is equal to the part with B. This is what we call A intercept B, right? And we can add to the other part, which is A intercept B complement. See, B is the knife that cut into 2 parts, right? Either B or not B, okay? So it's either A with B or A without B. That is called the total probability rule, okay? Is it? I think this is something that you learn from your kindergarten, right? Just cut into 2 parts, right? You have a mooncake, you cut it, and then must be either you cut it into left and right, right? Must the mooncake on the right hand side, but the mooncake on the left hand side will be the mooncake. That's it. Nothing new, right? right? That is something I don't think that require a lot of mental calculation, right? If a mooncake here, your B is cut into left and right, right? The mooncake on the right, left, and mooncake on the right. That's it. Okay, that's the idea, right? This is the A, and if this is B, then will be A with B and way without B. Is that clear? So I'm not going to continue to see this. Here is what we call the total probability. Is if A is a partition, then B can be cut into into multiple pieces. So the idea is the following, right? Instead of cutting it into single cut, okay, consider the following. Right, it's very simple. So this is the table, and I have a mooncake here, right? Right, this is a mooncake. It's called B, I guess. I don't know, it's A, right? And then I have many cuts here, right? Maybe this is cut 1, this is cut 2, cut 3, so on and so forth, right? So that means this is B1, B2, B3, and B4, right? So that means that this whole thing A, right, should be equal to, right, this part, right, B A intercept B1, right? Maybe I use another color to signify that different, right? B2, right? Plus this part, right? A intercept B2, right? And I have a pink color, right? B3. Maybe I shouldn't use pink. I don't know what color. Yellow. Refreeze this one, right? Plus this guy, A intercept B3. And then I have I don't know what color, red, right? B4, right? And I add this guy, A intercept B4, right? So if I cut it into 4 pieces, right, then it just 4 pieces add together. The reason why we want to do this is because it is difficult to calculate A directly. So this is what we call divide and conquer. You divide them into small part. Each part you know how to calculate probability. That is usually the way we do things, right? So that is the idea behind this formula. Is that okay? So there's nothing new there, but when you work on the problem, you will know this is very useful. Okay. Now at the end, I think we cover this, and probably we don't have more time. So this is called the odd ratio. Okay. Odd ratio is defined as the following. Okay. There are 2 different versions of ratio. Usually, odd ratio means the first guy, okay, without specify, is in favor of event A. So if you don't say this, odd ratio for A means this guy. Okay. Unless they say against, then it's always the first one. Okay. Odd ratio means probably A over A complement. Okay. And you can see that if A is very likely, this odd ratio is large, right? Because when A is likely, this guy is large, and this guy will be small, right? Because 1 minus, right? So when odd ratio get to very big, then will be very big, right? Because the ratio will enlarge. So odd ratio, sometimes you can imagine that is things very likely to happen, right? And then it's a probability, but it's a rescaled version, right? And why we care about this part, right? Again, it's just reverse. But anyway, why we care about this odd ratio, right? Because say suppose odd ratio is 1, then it's 50-50, right? 1, okay? And why we care about that? Odd ratio is actually people what we call that in the gambling industry. Okay. And usually we call odd 4 to 1, which means that you bet $1. If you win, you get $4 back. You give me $1. If you win, get $4 back. If you lose, you get nothing. Okay. And a fair bet, okay, what we call fair bet will be if what we call the odds, okay, equal to this guy. So let's see the example. It looks like a tricky. Looks this example. Okay. So for suppose I roll the dice once. What's the odd favorable to 6? Okay. Remember, odd is probability of it over its complement, right? Probability of 6 is 1/6, right? So this 1/6, suppose fair, right? So what it means is 1/6 over 5/6 is 1 to 5. Okay. So if you have a casino, say, what would be the odds you should be, right? Suppose people bet $1 for 6. Okay. How would you say is fair? You have to give him $5. Right? You reverse it. Because it's 1 to 5. So it means that if you have to win $5, okay, in order to be fair. Right? So why we care about this? It is because, okay, it is because in the real world, there are many things from the casino, right? The casino that bet, not just the betting the random thing, but the casino or the stock market actually tell you what's an odd, right? Because there's I think in UK, the online casino, you can bet for anything. And or actually stock market also the thing, the option or the thing is actually giving the odd. And the odd itself, you think the casino market is fair or is efficient, some more or less is right. Then you have some idea what's probability, right? Whenever US election, there are people betting for who is going to win. And in that case, you can back out what's the market thing about who would likely to win and what's the probability, right? Actually, same as the horse racing, right? And the odds are keep moving. You look at I never bet, but I don't know. But if you look at the TV, the bet keep moving. And the odd, actually, the horse racing, they give you is look at how people think about who is likely to win, right? And odd is defined this way. Okay, so that is the application of odd is if you try to see if you have the casino data or the online betting, you can actually back out who's likely to win, right? The upcoming election, whether it's going to rain, so on and so forth, right? Because options and futures also have that kind of idea, right? Because you think the market is efficient, then it must be if someone going to bet this going to go up, the stock going to go down, then they equalize the odd. You can back out what the market think whether it's going up or going down, right? Suppose you can imagine simply, right? Look at the stock market index, right? And people are buying the put or putting the call, then you can calculate what is the probability that it's going to go down. Same idea here. But we don't have, that is out of the scope. But odd is available. You can always back out this. Okay. So because of today's bus, I guess I should let you go earlier, 1 minute earlier. So let's see you on Thursday.